planets the same size as ours, on orbits with temperatures such that water neither boils nor freezes. They'd be in the so-called habitable zone. And we'd like really to observe these planets directly, not just to infer their effects indirectly. But that's hard. To realize how hard, let's suppose that some alien astronomers with a powerful telescope were viewing our Earth from, say, 30 light years away, the distance of a nearby star. Our planet would then seem, in Carl Sagan's nice phrase, a pale blue dot, lying very close in the sky to its star, our sun, but many billions of times fainter. You're looking for a firefly next to a searchlight. But the aliens could learn quite a bit about it if they could watch it. The shade of blue will be slightly different depending on whether the Pacific Ocean or the landmass of Asia was facing them. They could infer the length of our day, that there were continents and oceans, the seasons, and perhaps something about the climate, and even by analyzing the faint light, they could infer it had a biosphere. We can't do that yet, but within 10 years, European astronomers will have the extremely large telescope. They're not very imaginative in their nomenclature. This instrument will have a mirror, a mosaic mirror, which is 39 meters across, which is bigger than the length of this room. And this will have instruments on it which will allow us to draw inferences about planets around nearby stars, planets the size of the Earth, and something about their atmosphere. And this is a wonderful enrichment of what we know about our galaxy, because what we've learned is that almost every star has planets around it, and there are probably literally billions of Earth-like planets in our Milky Way galaxy, although, of course, we can only see the ones which are nearby. Well, habitable doesn't mean inhabited. And we still don't know the likelihood of life. We know too little about how it began on Earth to lay confident odds on where it might be. We don't know what triggered the transition from complex molecules to entities that can metabolize and reproduce, which we call alive. Although we understand the Darwinian evolution from a simple life to complex life. It might have been a fluke, or it might have been inevitable given the right environment. We just don't know. Nor do we know if the DNA, RNA chemistry of terrestrial life is the only possibility, or whether other options like methane-based life could be realized elsewhere. Moreover, even if simple life is widespread, we can't assess the odds that it evolves into a complex biosphere. And even if it did, it might be unrecognizably different. I won't hold my breath, but SETI programs are a worthwhile gamble, because success in the search would carry the momentous message that concepts of logic and physics aren't limited to the hardware in human skulls. Some people, of course, think that we've found life out there already. I get letters from people who say that they've met the aliens, they've been abducted by the aliens. I write back saying, do they really think that if the aliens had made the effort to come here, they'd make a corn circle, meet one or two well-known cranks and go away again? It doesn't seem very likely. And the second thing I tell these people is to write to each other and not write to me. Well, back now to stars and galaxies. They're much simpler than anything in the biological world. We know something about the life cycle of stars. New ones are forming in places like this, the Eagle Nebula. And we see stars dying. This is what the sun will look like in about 6 billion years when it runs out of fuel. And here's another star dying. But here is the remnant of a massive star. This is the famous Crab Nebula, which is the debris from a supernova witnessed and recorded by Chinese astronomers in the year 1054 AD. And this was the record where the Chinese court astronomer told the emperor that a guest star had appeared and was brighter than the moon. Well, in 1967, in 1968, we learned that in the center of this nebula, there is a little star, a neutron star. And Franco Pacini, as was said, before this discovery, was already thinking about neutron stars and was the first to realize, again, that they were able to generate energy if they were spinning and were magnetized. He had a picture in mind rather like this. You have a star which has a magnetic field and is spinning, and this produces energy. And this is the explanation, as we now know, for why the Crab Nebula is so blue and bright nearly 1,000 years after the explosion. And this, as was said by the President, is his greatest piece of foresight. Franco realized before this discovery that this was a way in which we could detect neutron stars. And this is a nice compilation of 3 key people. Franz Zwicky, who speculated about this even earlier, and Oppenheimer, who in fact did some pioneering work in 1939 on gravitational collapse, and had he not been diverted by the war, may have done some of these things in the 1940s, and there Franco on the right. We do now understand the evolution of stars from their birth to their death, and low-mass stars leave white dwarfs as remnants, and stars above 8 solar masses, they end up exploding like the Crab Nebula and giving a neutron star. But very big stars leave something even more exotic than a neutron star. They leave a black hole. And black holes were first discovered in the early 1970s through detecting gas swirling down onto them, the gas coming from a companion. They were stars in a binary system. I'm just going to mention very briefly another reason why the Crab Nebula and objects like it are interesting. And this was realized by one of my mentors, Fred Hoyle. He realized that during the lifetime of a massive star, it's powered by nuclear fusion, and it generates energy by converting hydrogen into elements up the periodic table. And before it dies, it has a sort of onion skin structure where the hotter inner layers have been burned further up the periodic table. And Fred Hoyle, in collaboration with Geoffrey and Margaret Burbidge and Willie Fowler, they were shown here on Willie Fowler's 60th birthday, they showed that this process was able to account for most of the elements of the periodic table that we are made of. A star explodes. The expanding debris contains these enriched elements, and then it condenses into new stars. So we are literally the ashes of long-dead stars, or if you're less romantic, we're the nuclear waste from what made stars shine. And this was a wonderful realization made by these people, which makes the Crab Nebula and things like it even more interesting. Well, let's now expand our horizons beyond our Milky Way to the extragalactic realm. If you could get 3 million light years away from our galaxy and look back at it, it would look something like this picture. This, of course, is Andromeda, the nearest big galaxy to us. It's a spinning disk viewed obliquely, where it's 100 billion stars orbiting around a central hub wherein lies a massive black hole. Here's another galaxy, this one viewed face on. And we have huge samples of galaxies to study. This is a picture of a slice of the universe out to about 400 million light years. Show every dot is a galaxy, and you see the galaxies are grouped into clusters. Well, how can we actually learn or understand much about galaxies. If you're a particle physicist, you can crash particles together in an accelerator and see what happens. Astronomers can't crash real galaxies together, but they can do experiments in a virtual universe. They can ask, what would happen if two galaxies crashed together? And here's an example of such a calculation of what happens to the stars and gas. You get a sort of train wreck like this. And when we look in the sky, we see things like this. This is a pair of galaxies in the sky, and it looks as though if we were to come back in 100 million years, they would have merged, because already the gravitational pull of one is pulling out a tidal plume on the other. These have got dangerously close. So it's by doing these simulations in a virtual world that we can understand galaxies, because we do simulations making different assumptions about the mass of stars, gas, and dark matter, and see which matches the data best. And incidentally, as a warning, the Andromeda galaxy is going to crash into our galaxy, just like in that movie, but not for another 4 billion years. So we can not only learn about galaxies by doing simulations, but we can also test ideas on how galaxies evolve by seeing them when they were young. Because when we look at objects a long way away, the light had to set out a long time ago. And this picture here shows a very small patch of sky. It would look just black with a small telescope. But each of these smudges is a galaxy. Many so far away that their light set out about 10 billion years ago. And so we can observe galaxies as they were 1 billion, 2 billion, 3 billion, 4 billion years ago, and test our theories that way. We can do better than geologists. We can actually observe the past. And this is a patch of sky so small it would take 100 patches like it to cover the full moon. And just as a slightly technical image, let me show the spectrum of the particular object highlighted there. This is a tracing of an optical spectrum, and the physicists here will note that the Lyman alpha line of hydrogen, which is normally in the far ultraviolet, 1216 angstroms, is here in the infrared. It's been stretched by the expansion of the universe, by the redshift, by a factor more than 8. And this is one of the most distant objects we can see in the universe. This is actually not a normal galaxy. It's a galaxy where the light from all the stars is being outshone by the light from glowing gas, excited by the black hole in the middle. If a black hole is fed with gas, it gets very hot. The gas gets very hot and magnetic fields get very strong, and this can give rise to radiation, which is much more intense than the starlight. It's what's called a quasar. And again, Franco Pacini thought about this. In fact, one of my joint papers with Franco was called Rotation in the Universe, and it was to show that rotation is a source of energy, not just in neutron stars, but in disks spinning around black holes. Well, we can look back to a time when galaxies were very young. What about a time before any galaxies had formed? The key evidence about the early universe was found by these people, Penzias and Wilson, using a radio telescope at the Bell Telephone Labs. They found that intergalactic space isn't completely cold. It's warm to about 3 degrees above absolute zero by weak microwaves, known to have an almost exact black body spectrum. Here's the spectrum here. This is, as it were, the afterglow of creation, the adiabatically cooled and diluted relic of an era when everything was squeezed hot and dense. It's one of several lines of evidence now which have allowed us to firm up the so-called hot Big Bang model. And here's the time chart for it. But first, let's address a fundamental question people raise about this. Our present cosmos manifests a huge range of temperature and density, from blazingly hot stars to the dark night sky. And people sometimes worry about how such intricate complexity could emerge from the sort of hot, dense, amorphous fireball. It might seem to violate the famous second law of thermodynamics, which describes an inexorable tendency for patterns and structures to decay or disperse. But the answer to this seeming paradox lies in the force of gravity. Gravity enhances density contrasts rather than wiping them out. So a patch of the expanding universe was slightly overdense would lag behind more and more because it feels extra gravity and eventually stop expanding and separates out. And this movie shows a simulation of part of a virtual universe. The expansion is scaled out, so the picture stays the same size, but you can clearly see the incipient structures unfolding and evolving. The blue is the dark matter, 5 times more than the ordinary atoms, and the red is the atoms themselves, the gas, which can radiate, dissipate, and form stars. So this is a simulation of how a galaxy is formed. So movies of this kind portray how galaxies emerge and how in galaxy-scale clumps, gravity enhances the contrast still further, gas is pulled in, compressed into stars. Each galaxy is an arena within which stars, planets, and perhaps life can emerge. And there's one important point. In this simulation, you've got to have some starting conditions. And those that are fed in weren't arbitrary. They came from observed fluctuations in the early universe, which have been measured by the Planck spacecraft, a famous European spacecraft. And this shows a contour map of the regions which are above average temperature and below average temperature. And you can analyze these fluctuations, and they tell you what the density contrast is on different scales at a very early stage. And you put that in your computer, you run it forward, and you can find out what the present density contrast is on galaxies and clusters. And the good news is that the data which tell us the RMS density fluctuations at different scales, plotted vertically there as a function of scale, they agree with what is predicted from the observed fluctuations, which is the curved line there. So there's a definite connection between the fluctuation we observe in the early universe and the structures now. It does seem that the present universe emerged by gravitational clustering. Here's the time chart of cosmic evolution again, from hot dense beginning to today's complex cosmos. We can trace back to 1 second. Indeed, we can probably be confident back to about a nanosecond. That's when each particle in this amorphous, dense early universe had about 50 GeV of energy, as much as can be achieved in the biggest accelerators like the LHC. And at that time, the entire visible universe would have been the size of our solar system. But questions like, what caused the fluctuations? Why does the universe expand the way it is? And why does it contain the observed mixture of atoms and radiation and dark matter? These questions can't be answered unless we can go back to the even briefer instance when the universe was hugely more compressed still, where experiments offer no direct guide to the relevant physics, which the particles have far bigger energy than we can produce. And at this point, I should say, I'm going to say some speculative things. So I'll put up a hazard sign that this next bit is very speculative. I'm going to talk about a time in the very early universe. This is a nice old magazine cover, when the whole universe was compressed not merely to the size of our solar system, but literally that big. And according to some of the best theories, when the universe was a trillionth of a trillionth of a trillionth of a second old, it was indeed just that size. And there's a theory called the inflationary universe, which says that the entire volume we can see was a hyperdense blob of that size. And indeed, it inflated from something even smaller, smaller even than the atomic nucleus. Well, the details are unclear and they're speculative, but the generic idea of inflation has been corroborated and gives a compelling explanation of the scale and gross uniformity of our observed universe. and how the fluctuations which we see in the Planck data and which are the seeds for galaxies may have been imprinted at a tiny stage when they were just quantum fluctuations. There's a link between the very small and the very large. Here's another fundamental question. How large is physical reality? Well, we can see, as I said, literally billions of galaxies, but we know that the volume of the universe that we can see with our telescopes is finite. And that's essentially because there's a horizon, a shell around us, delineating the distance light can have traveled since the Big Bang. But if you're on a boat, you don't think that the ocean ends just beyond your horizon, which is a circle around you. Likewise, we expect that there are galaxies beyond our horizon, and which we can never observe even in principle. We don't know how far they extend. There's no perceptible gradient across our observable universe. If you look that way and that way, things don't differ by more than 1 part in 100,000. So that suggests that it goes on quite a lot further. Most people would say at least 100 times further. And it may go on much, much, much further still. So much further that every combinatorial option of aggregates of atoms is replicated. And we would all, somewhere far beyond the horizon, have avatars. It might be some consolation to know that if you make a bad decision, there's an avatar out there that got things right. We just don't know. But be it as it may, even conservative astronomers are confident that the volume of space-time within range of our telescopes is only a tiny fraction of the aftermath of our Big Bang. But that's not all. According to some theories, for instance, Andrei Linde's eternal inflation scenario, our Big Bang could be just one island of space-time in a vast archipelago. The bottom right shows symbolically in this cartoon the aftermath of our Big Bang, the part we can see, and the galaxies beyond. But that's just sort of one bubble, one island in an archipelago, as it were. And this is a fascinating idea that's been explored in detail, but is still speculative. The big question is whether the physical laws are the same everywhere. They're certainly the same in distant galaxies as they are here. We can take the spectrum of light from a distant galaxy, and the evidence is the atoms are the same, the electron mass is the same, etc. But over this far more excessive domain in size, we just don't know. And if we ask what is a challenge for physics and astronomy in the next 50 years, is to see which part of this decision tree is correct. Is there one Big Bang, or are there many? If there are many, are they all the same in terms of their physics? Or, as some physicists, and string theorists in particular, suspect, could the different Big Bangs cool down differently and be governed by different physical laws? In this grander perspective of the multiverse, what we call laws of nature will be just parochial bylaws in our cosmic patch. Well, if this were the case, then many patches would be governed by laws that wouldn't allow the kind of complexity that allows stars to form, allows a periodic table to exist, etc. Those patches would be stillborn or sterile. The laws prevailing in them might not allow any kind of complexity. Well, if physical reality really is like this, then it's a real motivation to explore counterfactual universes with different laws to see which of them would allow complexity and which wouldn't. This is what's called anthropic selection, to try and see what range of physical laws allows complexity, because this may be something we have to consider if we turn out to need to take the multiverse more seriously than we can now. I'd like to offer a flashback to planetary science 400 years ago in the time of Galileo. This is not Galileo, this is Kepler. And of course, Kepler famously had the idea that the Earth was unique and that its orbit was related to the orbit of the other planets by beautiful mathematics. He imagined the Platonic solids nested together and that the orbital sizes of the different planets were in these proportions. Now we now know that the planetary orbits are determined by very complicated environmental things. We think he was misguided to expect a simple explanation. It could be that what we now think of as the fundamental laws may be environmental accidents in the same way, but on a grander scale, on the scale of our Big Bang rather than the scale of our solar system. That's certainly a possibility. Some don't like the multiverse idea because it would render the hope for neat explanations of the fundamental constants as vain as Kepler's numerological quest to understand the solar system. But our preferences are irrelevant to the way physical reality actually is. So I think we should be open-minded about the possibility that there will be a fourth and grandest Copernican revolution. We've had the Copernican revolution itself, then the realization that there are zillions of planetary systems in our galaxy, then that there are zillions of galaxies in our observable universe. But we then realize that our observable domain is a tiny part of a far larger and possibly diverse ensemble. And we live not in a typical part of the multiverse, but a typical domain in the subset which allows complexity to develop. To address this question, we have to know a lot more physics than we know now, maybe more than we'll ever learn, so we may never be able to settle this question. But nonetheless, it is a scientific question, but what's needed is a well-corroborated theory which can describe the physics at the inflationary era, but which can be corroborated by some observations that we can make, like predicting the mass of the electron or something like that. About 10 years ago, I was on a panel, in fact at Stanford University, where the chairman asked us how much we would bet on this multiverse concept. He asked us to put it on the scale, would you bet your goldfish, your dog, or your life? I said I was nearly at the dog level. Andre Linde, who was on the panel, he'd spent 25 years on his model for eternal inflation. He said he'd almost bet his life on it. And later on being told this, the great theorist Steven Weinberg said he'd happily bet Martin Rees's dog and Andre Linde's life. Well, Andre Linde, my dog, and I will all be dead before this is settled. But it's not metaphysics. It's highly speculative, but it's exciting science, and it may be true. If one wanted a logo for this entire research area that astronomers do, I'd choose this one, an Ouroboros. It has the microworld on the left, the cosmic world on the right. And it depicts the interconnectedness of the very small and the very large, the inner space of atoms and the outer space of the universe. There are links between small and large, left and right. Our everyday world of life and mountains is determined by atoms. Stars are powered by fusion of nuclei within these atoms. And higher up in the picture, there's another left-right link I haven't had time to talk about. Galaxies are seemingly held together by swarms of subnuclear particles, which make up the dark matter. The left is the domain of the quantum. On the right-hand side, Einstein's theory holds sway. As you know, general relativity and quantum theory are the twin pillars of 20th century physics. But they haven't yet been meshed together into a single unified theory. In most contexts, this doesn't matter. It doesn't impede us because their domains of relevance don't overlap. Astronomers can ignore quantum fuzziness when calculating the orbits of planets. Likewise, chemists don't need to worry about the gravitational pull between the atoms in a molecule, which is about 40 powers of 10 weaker than electric forces. But at the very beginning of the universe, everything was squeezed so dense that quantum fluctuations could, as it were, shake the entire universe. And as I said, to really understand what banged and why it banged, and whether there are indeed many other big bangs, we need this synthesis. And that's symbolized gastronomically, as it were, at the top by the snake eating its tail, the very large and the very small merging. So there are two frontiers of physics, the very small and the very large. But the richest variety plays out on a third frontier, at the bottom. Neither very small nor very large, but very complicated. Insects, people, and mountains. And this third frontier is the most challenging of all. This is a famous flea drawn by Newton's least favorite colleague, Robert Hooke, a pioneer inventor of the microscope. I show this because I want to emphasize that even an insect, with its layer upon layer of complexity, is harder to understand than a star, where intense heat and compression by gravity precludes any complex chemistry. And indeed, it may seem topsy-turvy that astronomers can speak confidently about black hole collisions a billion light years away, whereas, to take the other extreme, theories of diet and childcare, which everyone cares about, lack almost any consensual progress. But that's not surprising. It's simply that our complex everyday world presents challenges even more daunting than those of the cosmos and the quantum, because of complexity. Moreover, a fundamental theory, even if we could achieve it, would offer absolutely zero help to most scientists. Calling it a theory of everything, as some popular books do, is hubristic and misleading. Biologists aren't held up by uncertainties of subnuclear physics. They're held up because the structures they're studying are hugely complicated. Incidentally, we are literally halfway, in a sense, between atoms and stars. The geometric mean of the mass of a proton and the mass of the sun is 50 kilograms, within a factor of 2 of the mass of everyone here. And so we need to understand the atoms we're made of and the stars that make those atoms, which are far more complicated than either. Well, this was a digression to highlight the unity of science, plus a sort of deferential gesture towards the 99% of scientists who are neither particle physicists nor cosmologists and work on this third frontier, the frontier of complexity. But I'd like to end by zooming in from the universe, or even from an ensemble of universes, to realities closer to the here and now. And to remember that Franco was not only a fine scientist, but of course a fully engaged citizen. So here we are, back to Earth. I'm often asked, is there a special perspective that astronomers can offer to science and philosophy? Well, we view our home planet in a vast cosmic context, and in the coming decades we'll know whether there's life out there. These are fundamental issues. But more significantly, astronomers can offer a greater awareness of an immense future. Let me explain this. This is a familiar time chart of Darwinian evolution, spread over about 3.5 billion years from the first life to our present biosphere of which we're a part. And this, I think, is part of common culture, maybe not in Kentucky or parts of the Muslim world. But most people who accept this still somehow feel that we humans are the culmination of the evolutionary tree. And that hardly seems credible to an astronomer. Indeed, to an astronomer, we're probably nearer the beginning than the end. Our sun formed 4.5 billion years ago, but it's got 6 billion years more before the fuel runs out. It then flares up, engulfing the inner planets, and the expanding universe will continue still further. It'll continue, indeed, perhaps forever. And to quote Woody Allen, eternity is very long, especially towards the end. So any creatures witnessing the sun's demise 6 billion years from now won't be human. They'll be as different from us as we are from a bug. And I think they'll be electronic, not made of flesh and blood. Post-human evolution, here on Earth and far beyond, could be as prolonged as the evolution has led to us, and even more wonderful. Darwin himself realized that this evolution would happen, although he didn't envisage how it might happen. And indeed, it may happen faster than Darwinian selection by actual technological advances. But a final thought. Even in the context of this concertina timeline, extending billions of years into the past and into the future, this century is special. It's the first when one species, our species, has the planet's future in its hands. Because there are more of us, we're more demanding of energy and resources, and we have more technological power. Our creative intelligence could inaugurate billions of years of post-human evolution, even more marvelous than what's led to us. On the other hand, humans could trigger bio, cyber, or environmental catastrophes that foreclose all such potentialities. So our Earth, this pale blue dot in the cosmos, is a special place. It may be a unique place, and we're its stewards at a especially crucial time, what some call the Anthropocene era. And that's a key message for us all, whether we're astronomers or not, and I think it's one that Franco would have resonated with very much. Thank you for listening. Right. Okay.
I'm very grateful to Martin Rees for this wonderful conference, and also for the very nice recollection of Franco. As far as Martin Rees said to take the airplane at 8:30 in this evening, I would like to ask only for short 2 or 3 short questions, no comments or statements and so on, but short questions.
Yes.
Yes.
I'm Leonardo Dini, philosopher of science. My question is your ideas about the future of the search on the theory of multiverse, like in John Barrow hypothesis, like in your speech. Thank you.
Mm-hmm. Yes. So you want, there are many variants of the multiverse, but my point is that it's not metaphysics, it's a serious scientific question. But the way we can settle it is if we can have a theory of physics which applies to the very, very early dense stage, and that theory can be tested and verified in other ways, if it predicts, say, the masses of particles that we can observe. I mean, I think it's a mistake to think that you've got to be able to test every prediction of a theory. Let's take Einstein's theory. We take it seriously because it's been confirmed in many ways, as you know. And even though, and we believe what it says about the inside of black holes, even though we can't observe there, because it's been verified elsewhere. And the best we can hope is that we may have a theory which could tell us that, say, Lincei's mathematics is actually correct, and then we would have reason to expect that other big bangs exist, even though we can't observe them. This may not happen. It may come out of string theory, and of course there's a question about string theory, whether, even if it's correct, it's beyond human minds. Because one point I like to mention, I discuss in my book, is that there may be some fundamental aspect of the physical world which our brains aren't up to, just as a monkey can't understand quantum theory.
Other questions?
Yes.
Yes,
Giancarlo, yeah. Yeah.
Well, you have raised a number of points, so we could stay here until tonight, but of course you have to leave, unfortunately. Now, you mentioned the fact that venturers should go to Mars.
Yes.
Did you took into account the competition among space agencies?
Yes. Well, that's a good question. The Apollo program, of course, was fueled by superpower rivalry between America and Russia. and it consumed 4% of the American federal budget in the 1960s. After the moon landings, the Americans cut their expenditure. NASA now gets 0.6%. They didn't have a big program. And that's why there were no footprints on Mars already, as there would have been if they kept spending at the same rate. Now, it could be that the Chinese will decide to have a space spectacular, and they could, they'd obviously need to go to Mars, because to assert superpower parity, it wouldn't be enough to do what the Americans did 50 years earlier. They'd have to do a further great leap forward and go to Mars, so they might. But failing that, I think that the only plausible future is the private sector, because they can take higher risk and do it cheaper. Let's think about the shuttle, which launched 135 times, and there were 2 crashes. Each was a national trauma in America, because they presented it as safe. They sent up a woman school teacher and all that. Now, Western government can't expose publicly funded civilians to any significant risk. The public won't stand for that. On the other hand, a private company, which explicitly is going to launch sort of thrill seekers and risk takers, could do this. And so that's why I think it will be risk takers, maybe with one-way tickets, who will be the first to get to Mars. Now, that would be wrong if the Chinese try to do it first, but it could be that no nation is going to do a space spectacular of that kind, in which case I think the only motive will be just thrill-seeking, and we should cheer them on. Yeah. But I don't think that ESA or NASA should spend money on it. Yeah. Because robots are getting better, and robots can assemble big structures in space, do mining in space and things like that. Yeah.
Any other short question? If not, we thank again Professor Pacini.
Right. Okay. Thank you very much.
Thank you very much.
Thank you. Right.